Obviously this has been thought about before the building has been designed, and they thought, well, rather than just having a straight facade, let's do something a little bit interesting. Let's angle the PVs to give them a better orientation in respect to the sun. Let's angle the glass to meet up with the PVs, create a bit of interesting architecture. Then of course here, you know, they've decided to do something interesting again, where the PVs don't occupy a large area of the glass, they're sort of embedded within it, but in this sort of pattern, so that's allowed an awful lot of light through. And then yeah, we've talked about balcony systems. This is making it visible. You know, it's the same job that a bit of toughened glass will be doing here. It's just that it's got PVs sandwiched in the middle, so it's doing something useful. So thinking about rooftops, you know, if we've got flat roofs, we can be sticking it straight on the top of the building. And there's other technologies now, you know, Stuart was talking about flexible PV. We're looking at, you know, like the dye-sensitised stuff that's produced on reel-to-reel. There are technologies now where PV can just be literally rolled out on top of a flat roof building and secured down. But then also, you know, we can, if we've got a large area, we can use angled mounts to orientate the PVs a little bit better in respect of the sun. And obviously this isn't such a clean look, but if it's not going to be seen, or if it's quite utilitarian, or if it's something like a, you know, supermarket where you've got a bit of facade around the outside of the roofs, you don't actually see, you know, the flat roof behind, that's something that could be a good option. And then you've got these solar slates. Now, this system is C21 by Solar Century, and they've designed a solar slate that integrates really well with the Lafarge concrete roofing tile. So the profile is exactly the same. These roofing tiles, they're just a standard stock item that comes from the builder's merchant. And the C21 solar slate, which is, you know, it's the same depth as the concrete tile, but it's obviously much wider. And they can be carried up and just, you know, screwed onto the roofing battens in the same manner as, you know, the concrete tiles would be hung on them. And the cables can be pushed through the roofing membrane and everything connected from the back. So that's quite aesthetically pleasing because it blends in well with the roof. And this system, this is in the US, and obviously in the US there's a whole different culture of building. You know, here we put Welsh slate on the roof and it lasts for hundreds of years, whereas it's obviously a bit more of a disposable culture in the US. You know, you think about, they use shingles a lot, you know, posh shed felt, that just get sort of put on the roof, and then they accept the fact that it's a very cheap material, but once every 30 years or so they're going to be ripping it off and replacing it with something else. And actually, you know, there's a conversation that we can come on to a little bit later. If you think about the life cycle of PVs, if you're integrating PVs with a slate roof, chances are the slate's going to last longer than the PV when you think about all of the you know, materials. So if you've got a building integrated slate that fits, you know, there's a consideration there that you're going to be replacing the PVs or trying to change them before necessarily the slates. Now you might accept and say, okay, we'll strip the lot at once, we'll use the slates again, but with a new PV in however many years' time it lasts. So there's a whole consideration if we're going to integrate PVs with building. Let's consider the durability of the technology. So here we go, solar slates, but integrating with American-style shingles. And so Stuart's talked about thin-film modules and flexible thin-film, and the fact that we could do really interesting things. You know, here's a building with a curved form. The flexible thin-film PV can follow that curved form. And here's something that's really interesting as well. We're talking about mounting stuff horizontally onto roofs. These are PV cells, and they've got little inverters where they've said, okay, we'll miss out a couple of solar cells from the top of the module. We'll integrate small little string inverters into each module. And the beauty of that is that if we mount them on the top of the module, obviously they're waterproof, ingress protected, all the rest of it, but we put it in a location where it's really easy to then service that module without necessarily having to lift it up off the roof, disturb the mounting system or whatever. So I think, you know, that's quite a smart design where someone's thought about that. There's a handout at the back and in your packs about different types of inverters and smart new technologies. But this has obviously been designed to be easy to maintain in this sort of commercial application. Now, a little bit less attractive. You wouldn't necessarily want them mounted on the side of your house with all the inverters visible, but on something like that application, commercial roof, flat roof, no one's going to see it other than if they're using Google Earth. Why not, you know? So direct mount PV, you know, there's different things to think about. It's going to be lower roof load if you can use the PV as the roofing material itself, because obviously you've not got the additional weight then of a roofing material, a PV mounting system and PV on top. It's reducing fixtures. Wherever you've got fixtures and penetrations, you've got the potential for failure and defects. And also, you know, there's less potential for wind load because your PVs are flush to the roof and sealed at the edges. There's no way the wind getting under that and trying to, you know, lift anything up or blow anything away. And so, you know, we can also do interesting things here with direct mount PV. You can see here that you've got PVs that are south facing. I presume this is in the northern hemisphere, which have got a nice angle so that they get optimum collection. But you've also, what you can't see is on the other side here, you've got glazing on the north face, allowing a little bit of light into the space below. So, you know, that's quite interesting with that sort of sawtooth. And the thing with BIPV, and this is where I think there's a real potential avenue for consultancy firms, is in joining up the thinking between the different trades within the building team. You know, because at the moment, you know, if it's a retrofit installation, you might get a firm that goes up on the roof. I think, did you talk about a little bit of this in your presentation at all? No, okay. So, yeah, you know, you might have one firm that goes up, puts your cells up on the roof. Whereas, if you're going to integrate it into the building, you know, there's got to be a lot more, you know, consideration of how things interlink. You know, the architect's designing the form of the building, how it looks, you know, the whole project management of let's get the PV in there and let's make sure that the trades know what they're doing and how to work around it. And then obviously, you know, there's the structural considerations about, well, if we put in additional weight or less weight, how's that going to affect the building structure? And then, of course, you know, you've got electrical services engineers and facade and roofing contractors that are then going to go up and, you know, put the materials on to make the building watertight. And so, you know, if you can provide this full service and integrate all of these trades together, then, you know, there's a potential to really drive BIPV forward. And so the thing is to think about with BIPV is not just let's generate some energy by mounting something on this building, but how can we make that PV multifunctional? How can we get more value out of the fact that we're using PV rather than something cheaper like toughened glass? Now, what else is the PV doing? What's the additional function? Is it providing screening? Is it providing solar protection, which is stopping your building from overheating? You know, if you put in a piece of toughened glass which lets all the sunlight in, over the lifetime of the building, you might think, well, I'm going to be paying more for energy, air conditioning in the summer as a result of the passive solar gain. Whereas actually, if I put a PV in there to block some of the light or act as shading, I'm reducing that solar load on the building in the summer. I'm actually win-win, generating some energy at the same time. And actually, if I am using air conditioning or anything in the building, there's a really good correlation between the energy that's being produced by that glazed element when the sun is, you know, heating up the building and when I want the air conditioning, which is when it's hot outside. So, you know, it's thinking about those win-wins. Also, you know, architectural design elements, just making something look pretty, putting a bit of bling on the building, that sort of thing. But then also, you know, new products will be coming out that will integrate PV with, you know, insulation. You've got that additional roofing layer. It's stopping a bit of heat loss as well. You know, if you've got a sort of clever roofing system for something like a warehouse, you know, companies like Kingspan are starting to move into this market where they're looking at deploying PV, but they're also renowned for producing PUR foam insulation at the same time. So there's potential for emergence of some really interesting products. And obviously, you know, it's an impermeable layer. It's also producing, it's also protecting the building against the elements. That's the word that I was looking for. And also, you know, it's sound protection and insulation, if you want to consider it as another layer on the building that's stopping the ingress of noise. So it's thinking about all these things where you're not just using the PV as you know, an energy generator, you're getting some additional value from it. And so yeah, in conclusion, there's a real good future for BIPV. It's something that's growing, it's a real growth area. It's something that we can look at in the UK for high value added. And so yeah, it's improving the quality of the built environment. If we can get PV that blends seamlessly with buildings, as I think they've done quite a good job of with Optic, you know, it's generating energy, but it's doing it in a way that really enhances the quality of the built environment rather than detracts from it. So we're going to go back. I said there was going to be another quick presentation on glazed elements. Now some of these technologies are here already. Some of them are a little way off into the future, but this is the sort of thing that you should be expecting from the future of integrating PV into glazings within buildings. So Bogdan at lunchtime was talking about solar concentrators. And so the idea with solar concentrators is that you harness light from a very wide area, but rather than mounting PVs over that area, which would be expensive, you use a small quantity of PV at a point where the light is concentrated to. So you use a small amount of photovoltaic material, which is expensive. You use a large amount of glass if it's a lens, or plastic if it's a lens, or mirror material to reflect that light to that central point. And the idea is that the other material is cheaper. So you're using a smaller quantity of PV and potentially it's more cost effective. And also, it's something that's different visually. Now, there's an organisation called Desert Tech that have got the idea of doing this sort of thing in the desert. You might see there's some really big PV arrays in places like Spain, California, where you have lots and lots of mirrors mounted in the desert, very cheap, and they sort of track the sun, so they reflect the sun from the sky and focus it on a central tower, which is a bit like a lighthouse in reverse, if you like. Rather than being a tower that shines out light, it takes all that light from all those different mirrors. And there they use things like molten salt, so they can get salt so hot it becomes molten. And they pump that around the circuit, and then they've got heat exchangers where that salt can then raise steam, and that steam can then be used to turn a turbine and generate power in a conventional way. So that's how solar concentration might work on a really large scale, but obviously that technology is inappropriate for buildings. We need things that work on a much smaller scale. And so we've got this idea of organic solar concentrators, which are a bit like, I used to play with Lego as a kid, and I remember there were these bits in one of the Lego kits that I got that just absolutely amazed me, because it looked, in ambient light, it looked as if they were glowing, as if there was a little bit of light at the end. And they were like a sort of fluorescent green plastic, and they acted as a waveguide to take the light from the sort of wide area, and because of their shape they concentrated it towards the end where it appeared to glow. It wasn't glowing, it was just capturing the light from a much wider area. And so if you look here, we've got these plastics here where they're taking light from across the surface, but the light gets concentrated at the edges, and the edges appear to glow. And so this is potentially where you could put thin strips of PV material in order to generate electricity from this window. And of course the great thing is that it's also semi-transparent as well. So the sheet of plastic is sprayed with a dye, and it acts as a waveguide in combination. And so the edges of the sheet appear bright, and as we've said, that's what the PV captures. Now, there's a challenge with this, in that as the light hits the dye absorbs the light, and that causes the electrons in those molecules to jump to a higher energy level. And when they fall down back to a lower energy level, the dyes release that energy back into the plastic in the form of heat. So there's a bit of inefficiency there. But the light that doesn't bounces around inside the plastic in the same way that if you think about fibre optic cables, you can send light over vast distances for telecommunications, because the light bounces off the side in a process called total internal reflection. And this is what this sort of device is hoping to do here. Now, MIT, you've got about 80% of the re-emitted photons which are trapped within it. So that's where the inefficiency comes from. And MIT have looked at this and they've said, okay, there's a different way of looking at this. There's a couple of different things. So first of all, they're saying some of the light will go straight through, and so we could do something else by making a multi-layer device. We could put either something that captures solar thermal energy, a solar thermal collector, so we generate electricity first of all going through the solar concentrator, and then residual light is picked up by a much cheaper device. That obviously isn't transparent, it doesn't give you the window property. Or we could layer these devices and have different sheets with slightly different coloured dyes in to capture light at different wavelengths. But as I've said, where the dyes in this particular type of cell absorb the light energy, you get a little bit of heat produced, and that results in inefficiency. So MIT looked at it a different way, and they said rather than this sort of plastic with the dye embedded, we'll replace it with a sheet of glass and we'll coat that glass with the dye. And the special dye will re-emit light at a different wavelength from the wavelength that the dyes will absorb. And so this gets around some of the problem of reabsorption and inefficiency. But this is something for the future. It's not something that's going to be around immediately, but it's looking at the sort of technologies where scientists are starting to look for building integrated PV and for glazing. Now this is something that is a lot simpler. It's a much nearer term technology because this is just using, I presume it's crystalline silicon, the technology that we've seen. And what they're saying is if you think about Venetian blinds, that hang on one side of the window, lots of little slats with bits of string in between suspending them, they're saying, they provide a function of shading, and actually if they're all horizontal it's quite good because they capture that high summer sun but they allow the low winter sun to pass through. And so actually what about if rather than having a Venetian blind on the outside, and okay, it gives you flexibility, you can pull it up and you can change the angle of the slats and all the rest of it. What about if we made a double glazed unit with the glass, very wide and spread apart, and we'll have layers of PV running in between these two sheets of glass. So it looks very similar to a Venetian blind, it's just that it's inside the window and you can't change the angle of the slats or roll them up or whatever. But the great thing is, obviously, with a double glazed unit, if you keep the glass far apart, you provide a nice big cavity in there, which you can fill with air or you could fill with argon gas. But because of this wide cavity, you've got really good thermal properties to the window, so you're not going to be losing as much heat through the window. And you're stopping overheating in the summer because of the photovoltaic devices, they're acting as shading. And if you're looking through it on the level, you've still got good optical properties with the window. You can still see through it and look at the view outside. So this is something that's quite interesting and multifunctional. You've got that visual information, you've got diffuse light through the building, but at the same time, you're trying to prevent heat from entering the building in the summer. And so, it's stacked. It looks very much like a window pane, and here you can see some examples of the technology. Now, you've got it here in a window, but you've also got it here where they're integrating it into a roof line, and that's something that's very near to commercialisation. Obviously, I'm not sure if it is silicon or if it is thin film, but it's certainly something that's sort of here today. It will be reaching the market soon. It's something that can be done. Now, talking about dye-sensitised solar cells, we were talking about a company here called Dysol that makes this sort of solar cells. And here you've got a dye. Now you can actually, there's kits that you can buy where you can make this sort of dye-sensitised solar cell, also called Gratzel cells or excitonic cells, with a dye that just literally comes from crushed up blackberries or raspberries, and there's things in there called anthocyanins that fulfil the property that's required of this dye. I'm not going to go into the chemistry of it all because I don't think necessarily that's helpful, but the main things to take home about this technology is that it can be done on a roll-to-roll process. We saw what G24i were doing in the earlier presentation. It's one of those things where it's layers of material that can be deposited onto a cheap process in a continuous process. And also, you know, there's the possibility to make this flexible, and we've already looked at some of the potentials for flexible solar cells. Obviously you can't do that with a glass-based system. There's small amounts of platinum and ruthenium in the process, which are quite expensive, and that's something that they're working hard to eliminate. There's also problems with stability and degradation. You know, if you think about silicons PV, you know, a lot of thin film PV, it's very mature technology. People know that these cells are out there and that they'll last and that they're durable. However, at the moment, dye-sensitised solar cells aren't quite there. They don't quite last as long. However, obviously, there's really sort of clever people that sit in rooms and committees and talk about the developments and where the technology's going and what can be expected from it. So in the European photovoltaic roadmap, you know, they're really confident that these degradation mechanisms can be addressed in time with research, which is universities saying, give us more money. And you know, they're saying that actually, if we can overcome some of these challenges, they can really start making a contribution to the PV generation mix by 2020. So, you know, interesting possibilities with this technology. Now, another thing is, people are looking at carbon. You might have seen sort of carbon nanotubes, buckyballs, these sort of things. And people are looking at honeycomb patterned thin film devices. So the idea is that you've got a lattice here of a sort of carbon-based structure that you then deposit thin film material onto. And the thing about this technology is that the thin film clusters around the carbon structure, which is the sort of hexagons, but you've actually got the spaces in the middle of the hexagons that are perfectly transparent and you can see through. And it's a bit like, if you think, if any of you, Ford use this technology quite a lot in their cars with quick, clear windscreens, where you've got sort of, you know, the laminated toughened glass of the windscreen, but you've got sort of a very, very fine filament inside it, you know, and that fine filament can obviously heat up, defrost your screen very quickly, but it's sufficiently fine that if you take a step back from it and you're not really looking for it, you know, you can't see it, the window appears clear. Obviously, you know, like the DVLA and everyone else is happy with that sort of technology, so why wouldn't you want it in your home? So this is the sort of thing they're going on, large scale patterning and all the rest of it. The other thing is, we can look at DC a little bit later, and there's a real thing we saw in the exercises yesterday in system design considerations, that obviously if you can make use of the DC directly, you haven't then got that inverter loss factor of having to go from DC to AC and lose a little bit of the electricity in the process as heat. Now this Japanese company have said, actually, you know, smartphones and devices, everyone is using DC for sort of small electrical devices, and it would be silly to put all that energy from the PV through an inverter, lose a bit there, then put it through a little power adapter brick in the wall and lose another bit of energy again, only to have it back as DC to charge the device. They're saying actually we can do something really smart. If you've got a window, especially one that you might want to open and close, you know, you've got a point of failure there in terms of getting the electricity from the window into the building fabric. And so they say, actually, let's make this simple. Within the frame of the window, let's have a PV device, you know, semi-transparent if you like, so you can see through it. But rather than feeding that electricity back into the house, back into the grid, I don't know, they might have a small battery inside there or something like that. But let's put some USB sockets on the window, you know, so you can get your device directly. You know, if you imagine this room here, you know, if there was a little bench along the side or whatever, if we were in here and we knew that we were going to be charging a small electrical device, if this was an office or whatever, you know, plug your device into a USB lead, plug it into the window, charge it up from the light outside. You know, interesting idea, not going to work in every scenario, but certainly, you know, something that might gain a bit of traction in the future.